I'm Catherine Stevens from the American Chemical Society. Welcome to this news briefing from the ACS Fall 2019 National Meeting in San Diego. We're joined today by Dr. Sapna Sarapriya from Clemson University. She's studying how chipping away at ice forms could help keep windshields and power lines ice-free. Dr. Sarapriya?
Thank you, Catherine. It's a great pleasure to be here. I'm very excited. So I'll give you a little overview of what we are really trying to do. So our research is interested in understanding how liquid water transforms or transitions into solid ice. So, this is a very common phenomena. We experience it every day in our lives. You can see examples here on the slide from having ice on our cars, to having weather, climate, to preventing power line damage, also cryopreservation. And if you notice in these images, ice is always in contact with a solid surface. And this solid surface affects how this ice forms. But what we don't quite understand is what about the surface actually affects this ice formation. And that's the question we are interested in answering, right? We want to know what properties of a surface promote or hinder ice nucleation. Turns out this is a molecular phenomena and rather challenging to study in experiments. So we study this through molecular simulations, which gives us the spatial resolution, so we can see all the atoms at a time, and also gives us the time resolution to see what is really happening. Now, because we're using simulations, we can also change the surface properties one parameter at a time and really look into what is affecting ice nucleation. So we did that, and we've studied a variety of different surfaces, and I'm showing you a few examples here. So we looked at silver iodide surface, which is one of the best ice nucleators we know. And we changed its charge distribution, and we discovered that not only is the surface matching with ice important, but also the charge distribution plays an important role in the nucleation of ice on AGI. Then we looked at kaolinite, which is a mineral surface and is in our atmosphere. And we found that hydrogen bonding, as well as the orientation of the hydroxyl groups on the surface, play a very important role. And we are now looking at mica surface, which essentially was a choice that was motivated so that we can facilitate direct comparison and synergistic experiments and simulation studies to really, again, probe ice nucleation. So did we discover something interesting? We indeed did. So here what I'm showing you is the distribution of the angle between water dipole and surface normal for water molecules that are very close to the surface, so we call them interfacial. And the blue curves are for the surfaces that nucleate ice, and gray are the non-nucleators. And you can see that the blue curves have a very distinct behavior. They have a very characteristic behavior. So this tells us that we can use these molecular parameters to screen through these different surfaces and do it rapidly so that we can tell whether a surface is a nucleator or not. We want to now develop this parameter further to be able to screen through surfaces rapidly, but also maybe to develop techniques so that we can convert, let's say, a non-nucleator into a nucleator, or design surfaces that can do that for us. And we think this is the first step for us as we're moving towards engineering these surfaces for the ice nucleation behavior that we want to have in them.
Are there any questions? Please state your name and affiliation before asking your question.
Katie Cottingham, American Chemical Society. So it seems surprising that we still don't know exactly how ice forms. So why has it been such a challenge to figure that out?
We live, we drink, we breathe water a lot, right? Water is everywhere. But turns out water is really difficult to study. Even in liquid water, we don't know a lot of things. Then when you start putting liquid water in other solutions, in contact with other things, it just is hard to study because it's a very fine balance of various interactions. And now when you think of phase transition, it makes it even harder. So it's actually, part of the beauty of water, it's very hard to study, but I think that's also part of why it supports biology and is such a remarkable molecule. In terms of ice, the bigger challenge is a lot of the initial work has come from atmospheric chemistry, where they've looked at different surfaces. But when you go into saying, I really want to study a clean surface, and I want to observe nucleation is just really hard to do. Almost always the surface has defects or contaminants which are very hard to characterize. So that has been a challenge from the experimental side to find that really clean set of data, although we have some very remarkable data. From a simulation perspective, we've only now got the computational power to be able to study them, the amount of power we need. And also we are developing methods that allow us to do it. But still the bridging of the two is hard, again, because of surface defects and other challenges. So we are getting there. We have made a lot of progress in the last few years, but we have a long way to go.
Also, so how could your work be applied to create like windshields that inhibit ice formation or stop ice from sticking to it?
Right. So if we understand what properties of a surface make a given surface an ice nucleator or inhibitor, right, then we can think about, okay, how do we take that properties and put them in the materials that we can actually synthesize? So some work that's being done in our group and some other groups is learning from antifreeze proteins or ice nucleating proteins. So these are proteins that are present in organisms to either prevent or form ice. And then we see, oh, these are the common characteristics here. Can we take this now and transform it into, let's say, a polymer surface or make small molecules that we could just put in water and prevent ice nucleation, for example? So that's the direction we want to go to. But to be able to do that, first we need to understand all these at a very fundamental level. And that's where we are. There are certain challenges in trying to just transport these things and we, from one level to the other, but I think we're getting there, and that's sort of the idea. Ultimately, once you can get those kind of materials, then the idea would be you can just put it as a coating and prevent ice from forming or sticking.
Okay. One last question for me. So how could your work be applied to improve weather prediction?
So in weather prediction, right, you want to know at what temperature conditions and at how fast the ice is going to nucleate. Basically, then that goes into the models and it tells you, oh, you're going to have precipitation under these conditions. You do require a lot of different levels of modeling, but I'll just focus on what's relevant here. But if you know the composition of the dust, and I want to be able to predict how fast or how much ice will form, and if I don't really know how each of those surfaces affects it, then I'm not going to be able to put it in my model. So it leads to some kind of uncertainty. And that's what we are trying to understand so that then we can address those kind of uncertainties.
Sophie Rovner with the American Chemical Society. Can you give us a sense of how a surface that's a good versus a poor nucleator of ice, how they differ molecularly and morphologically?
That's a question we are trying to answer in our research. So we have some sense of it, but I think actually we just don't know exactly if we can say it is these surface properties, even from chemistry or morphology perspective, that makes one a nucleator or not. But the way we assess whether something is a good nucleator or not is how much do we have to cool the system before it starts to nucleate ice. So we all study that ice nucleates or ice forms at 0 degrees C, right? But it doesn't. You have to cool it down further when it actually kicks in and actually forms. Because if you go very slowly and do it very carefully, you can take pure water and cool it down to -40. And that's the same YouTube videos you see where they hit the bottle and you see the front of ice growing, right? So you can super cool water. But when you have these kind of surfaces which want to nucleate ice, you'll see that instead of it happening, let's say at -40, it'll happen at -5, -3 or something. So those are considered very good nucleators. So that's how it is assessed that it's a good nucleator or not. The other way is you can assess for a given temperature how fast does it nucleate. If it nucleates really fast, then it's a good nucleator. So some of the ideas that we have got from our studies is that really the key is in balancing the interactions in a manner where the water structure very close to the surface can be more ice-like. And what that means is that they have to have the right sort of density in some sense. So we all know that ice floats on water. So ice has a lower density than water. So the molecules have to arrange such that they can be that little less closely packed, if you will. And then also, water has an oxygen and two hydrogens, and the hydrogen bond, and that's what keeps the structure together. So they have to be able to orient to form that network of hydrogen bonds well. And that's where this molecular parameter concept comes. That's what inspires us to think about building such parameters. And so, a combination of the density and the orientations is what we have built a parameter for, and we think that helps. So it's a combination of various surface properties that can lead to the right interfacial structure for water, I think, is what our research indicates.
All right, thank you. And the press release talks about applying your work to improve weather prediction. Can you tell us a little more about that?
So that's what I was answering the last question as well, is, there are dust particles in the atmosphere. They are part of your cloud, and they basically help water change its phases. So if water goes up into the atmosphere as vapor, and then it can condense either as liquid or ice, or what is called a glassy state as well. And depending on what the surface is, it can accelerate one of these transitions. So if we think about transition of water into ice, and then the effect of each of these dust particles, that's the piece we are trying to answer. So that's referred to as heterogeneous nucleation, and we have to have a way of being able to predict under what conditions that will happen, what temperature is needed, what are the other conditions that are needed. So that's what we want to be able to predict and then improve, because we don't understand it right now. The models don't do as good a job as we would like for it to do.
Bela Buslig, ACS. Is there a preferred crystalline structure of the particles that nucleate better than others? And there is another issue here. The surface hydrophobicity or hydrophilic nature. Apparently, there's a problem where if you make a very hydrophobic surface, of course, it will be difficult to nucleate. But on the other hand, pollen, for example, has a very hydrophobic surface, so they stick to the other part. So basically, is there something that you can tell us to which would prefer or dissuade crystallization or?
So that's a really good question, right? In terms of whether a particular crystalline structure is preferred or not, that's another piece of the puzzle that we don't fully understand. So we have some surfaces where you form the traditional hexagonal ice, which is the most stable form of ice. But there are in other cases where other phases of ice become more favorable. And in some other cases, you find a mixture of these structures. Now, which structure forms is also not very clear. It really does depend on how the water and the surface interacts. And that also leads into the uncertainty in terms of weather predictions and stuff, because each of those water structures have slightly different properties. Now, hydrophobic surfaces have often been quoted as being anti-frost or de-wetting, or not letting ice stick to a surface. And it's true, because they don't let water stick, so they don't let ice stick, and sometimes that's very effective in sort of preventing ice from sticking on a surface. When it comes to nucleation, we have some early results where, in fact, a hydrophobic surface seems to be better nucleated than a hydrophilic surface, which surprised us. And this has been seen in a few other studies on model surfaces too, and it boils down to, again, the slight interplay of interactions and what water interfacial structure does. It just seems to just keep boiling down to that, because it's such a delicate structure that a little bit here or there can disturb that balance. And when that balance is disturbed, then you change tremendously how happy it is to form or not form the ice on it. So I think what we're learning more and more and appreciating more and more is that these macroscopic properties like contact angle, which is basically used to characterize hydrophobicity, may not be enough to tell us whether they're good nucleators or not. So we can take two surfaces with the same hydrophobicity and show that one wants to nucleate and one doesn't want to nucleate ice. And it boils down to those molecular structures that they promote ultimately.
Thank you.
Thank you. The archived version of this session will soon be posted at bit.ly/ACS 2019 San Diego. Please join us for our next press conference at 1:30 p.m. on peptide hydrogels that could help heal traumatic brain injuries. Thank you.